Hello, this is a presentation on the paper entitled Realizing Physical Layer Security in Large Wireless Networks Using Spectrum Programmability. This is a video presentation for the IEEE Globecom 2020 workshops. The paper, this presentation is delivered by me. My name is Faisal Bouabs. I'm senior lecturer at the School of Engineering and Information Technology at the University of New South Wales in Canberra, Australia. I would like also to mention the co-authors of this paper whose names and affiliation can be seen on this slide. The motivation of this research is based on the popularity of wireless networks, which basically is now very widespread across a number of devices and a variety of applications. Wireless networks, however, are based on the broadcasting nature of the wireless medium, which exposes it to interceptions by malicious users. This vulnerability is usually addressed through encryption. So their data is encrypted, and of the chance that a malicious user managed to intercept it, it won't have the computation capabilities necessary to decrypt the data. However, there's always a chance where malicious user can gain the required resources to do that. In that case, physical layer security emerges as a very interesting approach to this problem. Physical layer security is based on the concept of a wiretap channel, which is essentially the channel on which the eavesdropper listens to the signal sent from a source to a destination across the wireless medium. According to physical layer security principle, if a source sends a signal, that signal received a legitimate user, here labeled as YN, the copy received by the wiretapper, i.e. the eavesdropper, is a degraded copy of it. So Zn is a degraded copy of Yn. And the more degraded it is, the better it is for legitimate receiver, which means there is better security between the source and legitimate receiver. This is more or less the principles of physical layer security. Now, we have to mention that so far, we're work on this topic stayed in the information theory domain. Because of realizing such concept requires addressing a number of issues. The most important are how to implement physical layer security on a specific radio access technology. What are the details that need to be taken into account in that context? Also, what will be the effect on the performance of radio access networks? All these problems cannot be addressed across the board. We have to look at these problems for radio access technologies and radio access networks separately. What we did in this context is look at Wi-Fi networks as a specific radio access technology and a radio access network because we have experience in this domain. Now, in the context of large Wi-Fi wireless networks, which we really think is the most susceptible to eavesdropping, you have large network consisting of a number of access points, and the legitimate station tries usually to connect to the access point that offers the strongest signal, which essentially means the closest access point. And that's usually the case in many large networks. However, in the presence of eavesdropping station, we believe that physical layer security can be implemented such as we select the access point that verify the following conditions. One is provide the most useful message to the legitimate station and provide the most useless message to the eavesdropping station. Meeting these two conditions is called secrecy capacity. So what we're trying to achieve here is to find the access point that offers the highest secrecy capacity to the legitimate station. To do that, let's present a model and make certain assumptions to implement this algorithm. First of all, the eavesdropping station is trying to connect between either access point N1 or access point 2. So just two access points are available in this case. The eavesdropping station is only detected N1 no. What we have is trying to measure first the channel capacity between the access point, the legitimate station, and each access point, and also the eavesdropping station and each access point, here denoted as CN1M, CN2M, CN1E, CN2E, respectively. Once we have all these measurements, the algorithm calculates C1 and C2 values, which are the difference between the channel capacity of the eavesdropping station and the access point N1, and the eavesdropping station and access point N1. C2 is the same to do with access point N2. Now, this difference is only calculated if the SANR measured at the station is bigger than the SANR measured at the eavesdropping station for the two access points. If this value is equal or lower, C1 is 0 and C2 is 0. So what the algorithm does when it calculates C1 and C2, it tries to find which one is bigger. If C1 is bigger, it connects the station to access point N1. If C2 is bigger, it connects the legitimate station to access point N2. So it's actually very simple from the theoretical point of view. Realizing this is a little bit difficult. Why? Because there are certain challenges that are very hard to meet with the current technology. One of them is gathering the information. To gather the information necessary to do the calculation and detect the access point, you have to have a global view of the network, and this is not possible if you look at it from the access point of view. Access points have a limited view of the network, and that's not going to be possible. You will argue we should go for a centralized approach, but current technologies in this context are fairly limited. So they either open source and limited in terms of capabilities, or offer much bigger capabilities, but they are vendor specifics, which means you cannot implement the proposed secrecy-based algorithm on the top of it. So overall, it's very difficult to realize this algorithm on existing technologies. What you propose is to use the concept of spectral programming, which is based on the Wi-Fi architecture, which was part of this EU-funded Wi-Fi project. The idea in the Wi-Fi architecture and spectrum programming is to extend SDN to Wi-Fi networks. So we propose a Wi-Fi controller that manages the access points, and we implement Wi-Fi network management algorithms on the top of it, which allow you to centralize the management and distribute it through the southbound API. However, what it does more than that is it does not only implement SDN through the data plane, but it also extends it to what we call spectrum plane. And the spectrum plane is a way of managing radio resources through the Wi-Fi controller. So it is an extension of the SDN southbound API to be able to manage the radio resources of the access point and manipulate their radio parameters. You can think of it as a combination of SDN and software-defined radio. So it offers the high-level programmability of SDN, but also the low-level granularity and radio resource management capability of software-defined radio. And this is very useful in the context of realizing the proposed spectrum, the physical layer security algorithm. So if you suppose that we have the secrecy algorithm on the top of the Wi-Fi controller, what we'll do is it will ask the Wi-Fi controller to take the necessary measurements that we described earlier, the sharding capacity between the legitimate station and each access point, and also the eavesdropping station and each access point, send them to the algorithm. The algorithm then does the calculations and selects the access point that is more suitable for the legitimate station and asks the controller to perform the association. To validate this work, we propose an adversary model based on a passive wiretapper. So the adversary is just trying to steal sensitive information. It's not trying to do anything actively malicious, but just passively malicious. And for that, it deploys several eavesdropping stations at the perimeter of the large Wi-Fi network. The eavesdropping stations have access to a channel that is a degraded version of the legitimate channel, which means essentially it's noisy and is not as good as legitimate stations' wireless channels. We evaluated the work through MATLAB. So we simulated a large Wi-Fi network consisting of 25 access points deployed through a large area and 200 legitimate stations, and the number of eavesdropping stations varying between 10 and 40 stations. The rest of parameters are described in details in the paper. For comparisons, we propose the conventional access point selection algorithm, which is based on RSSI, which you find today in large Wi-Fi networks. In terms of evaluation metrics, we focus on the following. The secrecy rate, which is essentially the transmission rate at which the selected access point communicate with legitimate stations. The channel rate, which is the communication capacity at which the access point, the capacity of the channel offered by the access point to legitimate stations, and the throughput. We varied the number of eavesdropping stations between 10, 20, and 40, and we calculated the channel rate and the secrecy rate for the LSSI-based and the secrecy-based algorithm. What we notice is that as the number of eavesdropping stations increases, our secrecy-based algorithm offers higher secrecy rates in comparison to the LSSI-based. However, when it comes to the channel capacity rate, the LSSI-based algorithm outperforms our secrecy base, and the difference becomes bigger as the number of eavesdropping stations increases. This is later also validated to the throughput. So we notice that LSSI-based algorithm offers a little bit better throughput than our secrecy-based algorithm, but then the difference becomes bigger as the number of eavesdropping stations increases. Which this means, essentially it means that our secrecy-based algorithm, which is based on physical layer security, offers a better secrecy rate than SSI, but this comes at the expense of capacity or communication performance. Essentially what we've done here, we identify the trade-off between security and performance. And this is quite encouraging because it means that there's a lot more of work we can do to improve the performance and keep the secrecy rate or improve it. And this, we have certain direction we can look into. Most likely, we'll be looking into techniques related to fine-grained radio resource management, radio diversity, using multiple antennas, and MIMO techniques. But we would like also to look into much more complex use cases, indoor versus outdoor, what happens in the case of reflections, and other problems in the future. Thank you for your time. Bye.